Assalamu alaikum dear students. Today we will learn the designing of a common emitter amplifier. While designing a common emitter amplifier, we will introduce another kind of common emitter amplifier in which we have no emitter resistance. To design an amplifier, we need the specifications from a user. The users asked us to design a common emitter amplifier for the first requirement is maximum undistorted AC swing. It means when he or she apply an AC signal, the output would be undistorted. The other specifications given by the user are he has a DC supply having 16 volt. There would be no emitter resistance. He want us to use a transistor having beta 300, IS 3.7 femto ampere, and he gave us the early effect voltage of 100 volt. Remember, its value would be in negative when we placed into the formula. VBE is being given as 0.7. If not, then we already know that for amplifier we usually take VBE nearby 0.7 volt. VT is 25 millivolt for room temperature. So the proposed or the required system would be of this kind, the amplifier. So here you can see we have a short circuit from emitter to ground. Only a wire, no resistance. Transistor having beta this one. We have this amplifier when designed means to find the values of these three resistances so that we can have VBE 0.7 and VCE and IC so that it must ensure VBE is still 0.7 and maximum undistorted AC swing means when the user want to apply an AC input signal, the output would be an amplified form of that input signal undistorted, not clipping from positive side or negative side. We will see later, inshallah, as this lecture will progress. So to do this, it means we have to design this amplified circuit for this DC. So at this time we are actually going to bias the DC supply for this circuit. Last time we have been given these values and we analyze the circuit that where its operating point is. But now we are going to decide the biasing, the Q point and the load line, and then because of from that load line we will find these resistances. So the DC equivalent would be looking like this as we proposed in the last slide, and to design it as per the user's requirement we have to place a Q point on the characteristics axis. A Q point, basically a Q point on input axis for VBE 0.7 and at output axis. So it would be we have to place Q points on characteristic axis. So we know that input characteristics curve for a BJT and PN at the moment, VBE and IC curve, VCE and IC curve as at the output side. So at this time we don't know where Q point would be. So we have to place this Q point to fulfill the user requirement. So whatever we already have from the user, we can place it, and we have to actually do all the steps, maybe from reverse direction, but similar kind of steps that we have performed during the analysis work previously. So we have VBE is equal to 0.7 from the user, right? And it's okay, whenever we will find this Q point for this 0.7, we will get this IC, and we will see how we will decide the value of this thing. But once it is decided, then we would be having load lines. So let's see what would be the load lines. So whatever would be the load line, if we actually found the load lines, we will be able to get the slope of that load line. And that slope, we knew in our last analysis that it's nothing but the resistances within that loop. So this input would be load line. Input characteristics curve will give us the resistances of the input loop, and this, the slope of this output load line, will give us the resistances of the output loop. So what we have, we know that whatever would be the load line at the output side, the cutoff point is always VCC. So we know that, so just put it here so that we will know that what we already have and where we have to put our efforts to find the required parameters. So we have this VCC, right? So we know that the one endpoint of the output characteristics curve is at VCC, and we already have this value, so it would be VCC. So what about the first point, the maximum undistorted swing? So do you think we have to place our Q point here or here? No, because when we put our Q point here, and when an AC signal will make a swing of this VCE and IC, then it will clip first from here. Although it will give a full swing here, but it will cut at this side. So it would be better to place the Q point, the required Q point, at the center of either this side or this side. Is the same. But remember from our last lecture that it should not be from zero. The center of the active region. So active region starts from V saturation, maybe nearly 0.3, right? So 0.3 and 16, the midpoint of this thing. So we have found this midpoint, 16 minus 0.3 divided by 2. So it means our VCE would be 7.85 volt. So luckily we have found the Q1 or one coordinate of the Q point at the output characteristics load line.